Hello everyone, so in this video we are going to cover assignment problem on Hungarian method in solving the assignment problem. So assignment problem is a special class of transportation problem in which supply and demand is equal to 1 and the matrix is squared. So each variable is a binary decision, which means it only chooses 0 or 1, and all the constraints are in form of equations with equal signs. So here we have the problem. In a construction site, there are 4 cranes. Each crane must be allocated to one job. The time required to set up each crane for each job is shown in the table. So we are to find the best assignment of each cranes to the jobs so that the total time required is minimized. So in the problem, we are given the table that shows the time required to set up for each crane to one of each jobs. For example, for crane 1, it has a setup time of 4 for job A. So the first step in solving using Hungarian method is the row reduction. So we are to find the minimum of each row. So after finding the minimum of each row, we are going to subtract it from each row. So after we subtract each minimum row from each row, we obtain this new table. So from this new table, we are going to do a column reduction. So in column reduction, we are to find the minimum for each column. So for in this column, we have 2, 0, 0, and then 1. After subtracting each minimum to each of the column, we now obtain this new table. So from this table, we are to cover all the zeros. So after covering all the zeros, we now have 3 lines to cover all the zeros. So in that case, the number of lines is not equal to the number of m. So therefore, this is not yet our optimal solution. So we proceed to, from the uncovered lines, we identify the minimum. So the minimum of the uncovered lines will then be deducted to each of the uncovered lines. So the minimum of the uncovered numbers is equal to 3. So each of these numbers will be deducted with 3. So 3 minus 3 will then equal to 0, 1, 4, 1, 1, and 7. So since here 6 and 1 is under the intersection of 3 lines, so 6 will be added with 3, which is the minimum of the uncovered numbers. So this will then be equal to 9, and 3 plus 1 and 4. So from this new obtained table, the zeros are covered with lines, and then we are going to repeat what we do in this table. So we are to find from the uncovered numbers, we are to find the least, which is equal to 1. So each of these uncovered numbers will then be deducted with 1, and for this intersection, this will be added with 1. So now we will have this new values. So since this value is 0 and it is under an intersection, so it will gonna be added with 1, so this will become 1, and for this 4 it will now become 5. So after this we are going to cover the zeros. So first is this one, and then these zeros, and then these zeros, and then these zeros. So now we can conclude that we can now find our optimal solution. So with that, we are going to find the optimal assignment of each crane to each job. So from here, our optimal table, we can now assign each crane. So crane 1 will be assigned.
Transportation problem is a specific case of LP concerned with scheduling shipments from sources to destinations so that total transportation costs are minimized. There are three ways to solve for the initial solution. In this problem, I will be showing northwest corner rule and minimal cell cost method. First, you have to develop an initial table arranging the data in tabular form. So for the northwest corner rule, this requires us to start in the upper left hand cell of the table. Exhaust the supply and demand by allocating the least units possible. Between 90 and 50, we are to allocate 50. If the supply or demand are met, crash out the column or row. Then, repeat until the supply and demand are met. This is the initial solution. Solve for the total cost. Summation of the product of units shipped per unit cost. Now for the second method, which is minimal cell cost method. First is to develop an initial table. Then we are to start at the least cost cell. Then assign the smallest unit to the cell. And repeat until all cells and allocations have been assigned. This is the initial solution using minimal cell cost method. Solve for the total cost, and the total cost is $2,090.
The objective of a shortest route problem is to find the shortest distance from one location to another. In a network, this often involves determining the shortest route from one node to each of the other nodes. The shortest route technique can be used to minimize the total distance from any starting node to a final node. The technique is summarized in the following steps. Number 1, find the nearest node to the origin. Put the distance in a box by the node. Number 2, find the next nearest node to the origin or plant and put the distance in a box by the node. Number 3, repeat this process until you have gone through the entire network. The last distance at the ending node will be the distance of the shortest route. So for this problem, we are to solve for the shortest route, this figure. Looking at this figure, we can see that the nearest node to the origin, which is plant 2, with a distance of 100 miles. Thus, we will connect these two nodes. Now we look at the next nearest node to the origin. We check nodes 3, 4, and 5. Node 3 is the nearest, but there are two possible paths. Path 1 to 3 is nearest to the origin with a total of 150 miles. Then